All right, so click and close. I'm going to show you something really cool here. This is, there aren't very many, I don't do a ton of proof in here. Like you'll probably, maybe see more of that next year in college. But I tend to focus more on the, rather than the proof aspects of going through a lot of stuff, more of the application. But here's an example of one that I want to show you. We're gonna lean on this theorem called the squeeze theorem, which is an interesting theorem in calculus to prove a trig limit that we're going to use quite a bit. Okay, so the squeeze theorem just says this. It says, and let's talk about the language. This is a good opportunity to practice interpreting mathematical language before you get to college. That's a big deal. So if h of x is less than or equal to f of x, well, I should say it differently. If f of x is greater than or equal to h of x and less than or equal to g of x, for all x in an open interval containing c, except possibly at c itself. So that sounds a lot like the language we use when talking about limits, right? And if the limit of h of x as x approaches c is equal to the limit of g of x as x approaches c, and they're both equal to L, right? Then the limit of f of x as x approaches c exists and is equal to L. Okay? That's a lot of words. It's best summarized in a picture. Right? So we said that f of x was bracketed between h of x is the ceiling function and g of x is the floor function. Right? It's bracketed between those two functions. Everywhere on some open interval containing c except possibly at c itself. So one or more of those three functions might actually have a hole at x equals c. We don't care. We're just taking a limit. But if every place else on this open interval, the order is prescribed, g is above f, which is above h, right? Then can you see here that as if the limits of the red ceiling function and the blue floor function both converge at L when x approaches c, it's going to squeeze f down to that same limit. That's why they call it the squeeze theorem, or sometimes it's called the sandwich theorem. Okay? So, everybody see that? Okay? So we're going to do that to prove a really, really useful trig limit. If we take the limit, what does this evaluate to directly? The limit of sine, I'll call it x, limit of sine x, actually I'm going to call it theta. Not that it really matters, but the way I want to talk about it later. Limit of sine theta over theta as theta approaches 0. What does that directly evaluate to if I try to use direct substitution? And let me get everybody, let's close all those things up. I want everybody with me. This is pretty cool. I want everybody to get the benefit of seeing this because this is interesting. This is great math. 0 over 0, so it's more work, right?
Yeah.
So we've got to come up with a way of eliminating that indeterminacy. Well, there's no great way to do this. I mean, it's sine theta over theta algebraically would be really difficult. I mean, if I were going to try to do that, I guess I would probably use like I would use like the definition of sine theta in terms of exponential functions, and you'd use complex arguments of the exponential functions, and it would be a difficult process to do. And it would take a little while, and I think that would work, but it'd be hard. We don't want to do that. We're not ready for that now. So we want to come up with a different method of trying to eliminate this indeterminacy, right? We're going to use a geometric argument, really cool argument. So let's take the unit circle, and I'm only going to focus on quadrant 1 of the unit circle. So there's quadrant 1 of the unit circle, let's say, right? What's the radius of the unit circle? 1. That's what unit means, right? Unitary means of 1, so it's the unit circle has a radius of 1. And let's take some angle theta. So there's my angle theta. And let's build 3 shapes out of this. Okay, let's build a triangle that, we call this is going to be our blue triangle, whose base sits on the x-axis, has a base of 1. The vertices are going to be at the origin at the point where this horizontal line intersects the unit circle, and at the point where this ray that defines the angle intersects the unit circle. So it just looks like this. Okay? What's the area of that triangle? We'll make a list of these areas. What's the area of that triangle? Triangle, half the base times the height, right? You gotta come up with an expression for the height. So the height would just be, if I drop down that altitude right there, that represents the height, wouldn't it? Okay? So what is that? Let's just call it, for now, let's just call it h. How about? Okay. So if we call that h, can we come up with some trig expression that involves an h? Maybe we'll focus on this right triangle here. So the length of this leg of this right triangle up here is h. The length of that leg is 1. And what's the hypotenuse? 1. Yeah, good, because it's once again, that just represents, the hypotenuse represents the radius of a unit circle, doesn't it? The distance from there to there, it's a unit circle, so that's just the radius of the unit circle, it's 1. Okay? So then, what's a trig expression that's going to relate h to theta? What would be a convenient one? Think about SOHCAHTOA stuff. Now, we don't know the length of this leg right here, do we?
So we want sine.
So if we use sine, we'd end up with the sine of theta would be opposite over hypotenuse. That would work, wouldn't it? Because we know the opposite side has a length of h and the hypotenuse has a length of 1. We don't know the length of that side. It depends on the angle in a complicated way, right? So we could say sine theta equals h over 1, right? Which is just h. Oh, okay, that allows us to calculate an area for that triangle, doesn't it? Right? So now if we know that the height, instead of calling it, well, we can leave it as h, but really it's sine theta, right? H equals sine theta. So the area of the blue triangle is just going to be 1/2 times the base, which is 1, times the height, which is sine theta. Agree? So doesn't that just simplify to sine theta over 2? Okay, everybody with me? So that's the area of the blue triangle. Now let's do, how about we do a green sector. The green sector is just going to be defined, the sector defined by the angle theta. So that's just a piece of pi, right? Well, what's our formula for the area of a sector? Remember? The area of the sector is just going to be, you can always remind yourself of this, because like, what's the, here's how you can remind yourself. What's the area of a circle? Say it again.
I don't remember what it is, but I was 3 letters.
S equals r theta. There you go. Well, now that's arc length, right?
Yeah.
That's arc length, but what's area? Here's how you can think about this. What's the area of a sector? Isn't that just a piece? Think of that sector, and I know this sounds dorky, we're not in kindergarten, but that's just a piece of pizza out of a whole piece of pizza, right? Everybody agree?
Yeah.
Right, so it's just going to be, you're just going to take a fraction of the whole area of that unit circle, right? Well, what's the area of the unit circle? I mean, the area of the circle is just pi r squared, right? So it's just going to be pi times 1 squared. So the area of the unit circle is just pi, agree?
Yeah.
Okay, right? So then what fraction of the unit circle does theta represent? What's the total angle around the unit circle if I were,
360.
okay, but we want to use,
2 pi.
we want to use radians, so 2 pi, right? So out of the 2 pi available angle, right, we're only using theta of that. So theta over 2 pi?
Yeah.
Everybody agree? Okay, so we end up with something like, okay, so, hang on a second here, I gotta think. I just did this for class. Area is gonna be, Oh, yeah, right, so it's gonna be, that works, right, never mind. So we're gonna get theta over two pi times the pi r squared times pi, right? Because r is equal to one, so pi times one squared. So the pi's cancel, right? And I just get theta over two, everybody agree? Is the area of the green sector, okay? So, which is bigger? The green sector or the blue triangle? The green sector has a little bit of extra area, doesn't it, right? So we could say that that's true. Now, if theta approaches, if theta went to zero, maybe, who knows what's gonna happen, right? But for all values greater than zero, okay, agree? It's gonna be greater than or equal to, the green is always gonna be bigger than, never less than, always either equal to or bigger than, right? Okay, the other triangle we're gonna look at is gonna be, we'll make it a red one. Whoops, we're gonna do this. We're gonna make another right triangle. Okay, what can you tell me about this right triangle, this red one? So we're trying to calculate that area. The base is one, good, right? So we got a base of one. We just need the height. Okay, now what's a trig function here that we could use to maybe represent the red height? We'll just call it red h for now. That'd be a tangent, wouldn't it? Because theta, the tangent would involve the opposite, which is h, over the adjacent, which we know, which is 1. The hypotenuse we don't know here, but we know the other two, right? So we could say tangent theta equals h over 1, which is h, right? So the area of that triangle would be 1/2 times 1 times h, and h is tangent theta. So tangent theta over 2. Everybody agree? Okay, and we know that that one's going to be even bigger than the sector, greater than or equal to the sector, right? Okay, so we got this relationship. Let's do a couple things here. Let's go ahead, let's rewrite the tangent first of all in terms of sine and cosine, how about? So, and that's just going to be what, sine theta over 2 cosine theta? Okay. Okay, I'm going to multiply each of those. In quadrant 1, sine theta is always positive, right? I'm going to multiply each of those by 2 over sine theta. Okay? I'm going to multiply each of those by 2 over sine theta. So we get from this step to this step, multiply by 2 over sine theta. Okay, what's that going to give me? I think I need to go to the next page. Run out of space.
Cool. Whoa.
I like that. All kinds of great toys here. Okay, so what's that going to give me?
We're impressed.
If I multiply everything by 2 over sine theta, the first fraction becomes
1.
1. Okay?
This whole class do shows that.
Yeah, there you go. What's this one going to become?
Theta over sine.
Theta over sine theta, okay? And what's this one going to become?
2, or 1 over cosine theta.
1 over cosine theta. Okay, and I've got this relationship holds because I multiplied by something positive, right?
Yeah.
Okay. All right, now let's take the reciprocal of all those. Okay. So if I take the reciprocal of 1 is just 1. The reciprocal of theta over sine theta is going to be sine theta over theta, and the reciprocal of cosine theta, 1 over cosine theta, is cosine theta. What's that going to do to the order? A large number has a small reciprocal, right? Everybody agree? Like think about number. If I had the numbers 2, 3, and 4, when I take the reciprocals, 1/2, 1/3, 1/4. Well, now the 1/4 becomes the smallest, and the 1/2 becomes the biggest, right?
Yeah.
So I'm going to have to flip the directions of those inequalities. That's a property of inequalities, right? So we get this, okay? I'm just gonna rewrite that. So we're gonna say then that, I'm gonna turn this around, so we're gonna say that sine theta over theta is always gonna be greater than or equal to cosine theta, and less than or equal to 1. Okay? So that's always true in, that makes sense? That's always true for any angle we choose. So what happens now if we take the limits? If I could call this like f of x, let's say, and this is like h of x, and that's like g of x, and what did we say? I guess I got it backwards. G should have been the top one, but you get the idea. If I take the limit of all those as x approaches 0, let's see what happens. So the limit of 1 as theta approaches 0 is what? 1. Okay? The limit of sine theta over theta as theta approaches 0 is, we don't know. So we're trying to find. But what's the limit of cosine theta as theta approaches 0? We can evaluate that directly, can't we? What's cosine 0? So what is the limit of sine theta over theta?
1.
1, by the squeeze theorem.
Huh.
Right? That's important. Right? That's a theorem that we can use. That's a special trig limit that comes in very handy. So we end up with these 3 special limits. I'm not going to talk about that one. We'll come back to that one maybe later in the year kind of thing. But the limit of sine theta or sine x, whatever you want to call it, sine x over x as x approaches 0 is 1. Well, then just by using some trig identities, I'm not going to bore you with that stuff right now, but it's not hard to get the limit of 1 minus cosine x over x as x approaches 0 is 0. That kind of just stems from this one, just relying on some of the trig stuff you did last year, some of the trig identities. Not a big deal, but let's use this one. You don't use as much, honestly. And like at the end of the summer, I wouldn't even remember that one. This one I'll never forget. This one I don't remember. If I need this one, I just derive it from this. It's not, unless I'm teaching calculus, then I remember. But otherwise, I probably don't. But let's use this stuff. So what about something like this? I want to show you, and this is what I was talking about yesterday, that all these new AP Calc books, they don't cover this stuff, which is the dumbest thing in the world. This is important stuff. You really need to know this if you're going into physics or engineering. This is a kind of cool limit to be familiar with. So what about the limit of tangent x over x? If I try to directly evaluate that, what do I get? 0 over 0. Tangent of 0 is 0, and x obviously goes to 0. So it's indeterminate, right? So what can we do? Well, now that we have these special limits, we can use trig identities or relationships to try to rewrite this expression in such a way that one of these 2 limits, and it'd be this one in this case, you'll be able to see pretty easily, that one of these 2 limits is going to expose itself, pop out, and then that's going to reduce the indeterminacy. That's going to be the equivalent of canceling factors, right? So what do you think? You can probably come up with a strategy here. What do I probably want to do with that tangent?
Make it sine and cosine.
Sine over cosine. So typically we want to write the composite trig functions in terms of the fundamental trig functions, sine and cosine. You're used to that from last year, probably doing a ton of stuff like that, right? So we get the limit of sine x over x cosine x.
Yes.
Okay? Well, let's just split that into separate limits. Let's just write that as the limit of sine x over x as x approaches 0 times the limit of 1 over cosine x as x approaches 0. What does that limit approach? 1. Right? If I evaluate this one directly, what do I get? 1.
One.
So my answer is just 1 times 1, which is 1. See how that works? So we want to coax this special limit out because we know that even though that one seems indeterminate, that's one of our special limits we know how to evaluate, right? Do you have to write these as separate limits? I would say no. I would say if I were doing this work, what I would do is instead of doing that, I would just write this as the limit of sine x over x times 1 over cosine x as x approaches 0, and now I can evaluate those separately, rather than having to drag that limit notation. I mean, really, it's implied that that's what we're doing. We're taking separate limits, they're multiplying, taking the product of separate limits. Okay, let's try another one. How about that? So you might be thinking sine 4x, I gotta use my double angle formula or something, right? I could, which half angle, double angle? This one. Do you remember what the sine of 2 theta equals? 2 cosine theta, right? So maybe you're thinking you gotta do that twice, right? I've got sine 4x is sine of 2 times 2x. And yeah, I mean, you could do that stuff, but there's an easier way to do this. There's an easier way to do this one. Here's our special limit. I'm going to write it with theta. So if you look at these two parts, we've got the sine 4x over the x. Which part is easier to work with algebraically? The argument of the sine function, so the stuff that's trapped in the sine function, or stuff that's outside of the sine function? Outside. Because if you want to work algebraically with stuff that's inside, you got to use all these big trig identities, right? So we'd rather just leave that 4x. I'm going to leave it alone. That's our theta, right? That's our theta up here. What do I need to get on the bottom in order to have this look? If the theta is 4x, I need a 4x on the bottom, don't I? So how could I introduce a 4x to the bottom?
Multiply by 4.
Top and bottom, right? I got to multiply it by 1. I'm multiplying by the multiplicative identity, which is 1. So I'm not changing anything. I'm not changing the identity of the expression. It's still equal to that because I'm multiplying by 1. But I'm going to conveniently attach that 4x to the bottom. So if I multiply both the top and the bottom by 4, I'm going to get the limit of sine 4x times 4, right? I can put the 4 right there if I want to. Maybe we could even do better than that. On the bottom, we're going to get 4x. Okay, there's one other part that doesn't look right. The limit of sine theta over theta as theta approaches 0. Okay, is that a problem? That we've got the sine of 4x over 4x as x approaches 0? What do you think about that? How come? You're right.
Because 4 times 0 is.
Ah, okay, as x approaches 0, what does 4x approach? 0. So I can just do that. Right? I didn't change anything, did I? Right? And then remember this 4 right here. That's a constant, so I could just pull that out in front of the limit to make it look even better, right? So I could write this as 4, pull that 4 out front, times the limit of sine 4x over 4x as 4x approaches 0. And what's the value of that limit? 1. So I get 4 times 1, right? Yeah, the special limit goes to 1. And so we end up with 4. Make sense?